Hello everyone, it's Mrs. McCready here, and today we are going to go through C12 chemical analysis for triple science. We're going to talk about 4 different topics today: pure substances and mixtures, analysing chromatograms, gas tests, and also testing for positive and negative ions. Before we get started, there's a do now on the screen, so your teacher should pause the lesson here. You can tackle those questions and then you can come back and click play when you've finished. So those were just some simple ratio questions. If you didn't get those correct, it might be worth going over those simple mathematical skills again before you take your assessments. So we'll start this session by talking about pure substances and mixtures, the differences between those, and also some examples. So in everyday life, we often use the term pure, not in a chemical context. So you might talk about pure orange juice when you buy that from the supermarket. Now that substance isn't what we would call chemically pure, and you'll see why not in just a moment. So a pure substance is made up of just one substance. Now that can be an element or it can be a compound, but what's important here is that everything in that substance is just one type of substance. So for example, you could have something that is a pure substance made of an element, so this represents that. You can see all of the atoms are identical and we just have single atoms within that diagram. Our pure substance could also be made up of a compound. You can see in this diagram on the right-hand side, there are 4 molecules of a compound. This is still pure, even though we have 2 different types of atom here, it's still pure because it's only made up of that one type of compound. All the compounds in the box are the same as each other. And what's important about pure substances is they have fixed melting and boiling points, and this is one of the ways that we can test for purity. So for example, water will always melt at 0 degrees and boil at 100 degrees. So if we had a water sample, we could test whether it was pure water just by boiling it. If it boiled at a temperature anything other than 100 degrees, we would know it was not pure. When we talk about mixtures, they're made up of more than one substance, and you will have looked at mixtures throughout your education in chemistry. Formulation, though, is a new word to you this year, and a formulation is a specific type of mixture that has been designed to be useful. So, for example, paint, cleaning products, medicines, they all contain ingredients that are there for a purpose. So all formulations are mixtures, but not all mixtures are formulations. So for example, seawater is a mixture, but it is not a formulation because it has not been designed to be a useful product. When we think about the ingredients of these types of formulations, they're all there for a reason. So for example, in paint, you have a pigment which colours the paint. You also have binders to keep the paint together, and you have solvents to dissolve the pigment in the paint as well. So there's lots of different ingredients in formulations, but they're all there for a specific reason. The next thing we're going to talk about is analysing chromatograms. And you will have seen these before. They're essentially the pictures that we get from the chromatography experiments. You will have studied chromatography in C1 as one of our separating techniques for mixtures. But now in C12, we need to be able to perform some calculations to go alongside that. So you can see a very simple chromatogram up here on the screen, just of 3 different substances, A, B, and C. The way that chromatography works is it separates mixtures based on their solubility. So chromatography involves 2 phases. It involves the mobile phase, which is our solvent, usually water, and it involves the stationary phase, and that's our phase that stays still, usually paper. Now the different substances have different solubilities in the mobile phase, and the more soluble they are, the further they will travel up the paper. So that's how chromatography is separating out these different substances. If we don't know what a substance is, if it's an unknown substance, we can identify it by calculating its RF value. So that funny RF symbol stands for retention factor, and all it's telling us is how well it's dissolving in the mobile phase in chromatography. We can use a formula to calculate that RF value, and you can see it up here on the screen. So the RF value is equal to the distance moved by the spot divided by the distance moved by the solvent. I'm going to take you through a worked example for this one because sometimes it's a little bit tricky to see this on the diagram. So if our worked example had asked us to calculate the RF value of substance A, there's a couple of measurements that we're going to need to make. One is how far the spot has moved, and you can see that I'm measuring from the start line at the bottom to the middle of the spot A. The other thing I'm going to need to know is how far the solvent has moved. This time I'm measuring from the start line to the solvent front, which is where the solvent has reached at the top here. So those are my two measurements I'll need to know, and in an exam I would use a ruler to measure those two distances. I know this is my formula. The RF value is the distance moved by the spot divided by the distance moved by the solvent. And I just measure those two quantities from the arrows I've just drawn on my diagram. The distance moved by the spot when I measured that arrow is 2.1 centimetres, and the distance moved by the solvent is 6.2 centimetres. I pop those numbers into my calculator, I get an answer of 0.34. Now sometimes people will do this the wrong way round. Sometimes people will do the distance moved by the solvent divided by the distance moved by the spot. You'll know if you've got it the wrong way round because you'll have a number bigger than 1. The RF value cannot be more than 1 because the spot cannot move further than the solvent. So your number for your RF value should always be less than 1. If it's not, just check that you've done this calculation the correct way round. The final piece of revision that we're going to do today is on gas tests. Now these are qualitative tests that we can carry out to prove whether we've got a certain gas being produced in an experiment. The first test is for hydrogen. You can see in the diagram we have a boiling tube of hydrogen and we've got a lit splint being put into the bottom of it. The boiling tube is upside down, that's just so that the hydrogen gas doesn't dissipate into the atmosphere and that we get a better result. Now hydrogen is a flammable gas, and because it's flammable, when we put a lit splint next to it, we get a very small explosion, and that's what produces that squeaky pop sound. So a lit splint will give us a squeaky pop if we have hydrogen gas present. Next gas is oxygen. So again, we have our boiling tube here, this time it's full of oxygen, and we have a splint. The difference this time is that splint should just be glowing. It shouldn't actually be on fire, it should just be glowing orange. And the positive result is that because of that high concentration of oxygen, the glowing splint will actually relight and set on fire again. The third test is for carbon dioxide gas. And you can see here that the green arrow is representing carbon dioxide gas being produced in another flask or another tube and being bubbled into the test tube in the diagram. That test tube is full of lime water. If the gas is carbon dioxide, that lime water will turn cloudy. And the final gas is chlorine. You can see in the tube there is a solution generating chlorine gas. Now, if that gas is chlorine, it will bleach that piece of litmus paper at the top. So a piece of damp litmus paper will bleach and turn white if there is chlorine gas present. Okay, so let's look at the kinds of questions you might be asked about these 4 gas tests that I went through on the previous slide. Sometimes they'll be very straightforward and they will just say, describe the test for carbon dioxide gas or describe the test for chlorine gas, and you will know exactly what you have to do. Sometimes you'll need to do a little bit more work, and this is an example of one of those times. Have a look at this question. Hydrogen peroxide decomposes in the presence of catalase. This is the equation for the reaction. Describe how the student could test for the gas produced. Now you might be able to see this straight away, but if you don't know what the gas produced is, you're not going to be able to answer this question. So I need to go and look at the equation that they've given me to work out what the gas produced is. And what I'm looking for is the state symbol G. That symbol in brackets after the substance tells me what state that substance is in. And you can see that it is the O2 that has got the G symbol next to it. So that is the gas that's being produced. So I can decode this question as describe the test for oxygen gas. That's what this question is asking me. And then it becomes fairly straightforward. I know that the test for oxygen gas is a glowing splint will relight, and that's what I would write in my answer. So over the next 2 slides, we're going to talk about testing for positive and negative ions. So when we have an ionic substance, that is one made from a metal and a non-metal, we have positive ions and we have negative ions. The positive ions are always the metal ions, and we're going to talk about 2 methods that we can use to test for which metal ion is present in a solution or a compound. The first test we can do is called a flame test, and the basic instructions for this are going to come up on the screen. Your first job is to dip the nichrome wire, that's just a metal wire, in hydrochloric acid and then place it in the flame. The purpose of this is just to clean the wire, to get rid of any substances that are on there already that might interfere with the colour of your flame test. You then need to dip it back into the HCl again. That's just to make the wire wet so that the compound that you're dipping it into will stick to it. If you're using a solution, then you don't need to dip back into the HCl, you can just dip into the solution. Then you hold the loop of the wire back into the Bunsen flame and you note which colour it turns, and the colour will tell you which metal ion is present. This table of colours you will need to learn, and you can see the 5 in the table are the ones that you are interested in. So lithium, the flame colour turns crimson, that's a very dark red, sodium, yellow, potassium, lilac, which is a shade of purple, calcium turns an orangey red colour, and copper turns green. The other way that you can test for positive ions is using precipitate tests. Now, a lot of those metal ions in solution will actually combine with hydroxide ions from sodium hydroxide to form a solid. So the basis of this test is you just add some sodium hydroxide solution to your solution that contains your unknown positive ion. And the colour of the precipitate, the solid that forms in the test tube, will tell you what metal ion was present in that solution. And here are the colours. Say, for example, if you had calcium ions in your solution and you added sodium hydroxide, the calcium ions will combine with the hydroxide ions to form calcium hydroxide, which is a white solid, a white precipitate. And you can see there are 5 other colours other than calcium here that you need to learn. Calcium, magnesium and aluminium all turn white, copper 2+ ions turn blue, iron 2+ turns green, and iron 3+ turns brown. So that this precipitate is actually a metal hydroxide. So for example, if you had iron 2+ ions in your solution, they would combine with the hydroxide ions from the sodium hydroxide to form iron hydroxide, which is green. Now you might be thinking, well, 3 of these give us the same colour precipitate with sodium hydroxide. That's not very helpful, and you're absolutely right. But there's some further tests that we can do. So if we add our sodium hydroxide solution and we get a white precipitate, that tells us that our metal ion is either calcium, magnesium or aluminium. The first thing we would do is we would continue to add sodium hydroxide. So we would continue to add sodium hydroxide to the solution. If the white precipitate dissolves again, we know that the metal ion is aluminium. The calcium precipitate and the magnesium precipitate, neither of those will dissolve no matter how much sodium hydroxide you add. So that's our first step, is to add more sodium hydroxide. If the white precipitate dissolves, we know that the metal ion in the solution was aluminium. There's nothing further we can do with the precipitate test to distinguish between the calcium and the magnesium. However, they give different colours with the flame test. So if you got a white precipitate with sodium hydroxide that did not redissolve with excess sodium hydroxide, you would know that metal was either calcium or magnesium, and you could then perform a flame test to decide which it was. The other part of our ionic substance will be a negative ion. And that negative ion could be lots of different things, but the three we're going to focus on today are carbonate ions, halide ions, so chloride, bromide, iodide, and sulfate ions. There are others, obviously, but you don't need to know about them for GCSE. So our first test is for carbonate ions. All you have to do for this test is add a dilute acid. If there are carbonate ions in the solution, you will see fizzing, and that fizzing is the production of carbon dioxide gas. You could just double check by bubbling that gas through lime water, and you would see that the lime water would turn cloudy, proving that it was carbon dioxide. The second test we need to know about is testing for halide ions. In this case, we're only talking about chloride, bromide, and iodide ions. Your first step is to add some dilute nitric acid. The reason you're doing this is to remove any carbonate ions. I'll talk about why in the next step. You then add silver nitrate solution. And you're looking for a precipitate here, again, a solid being formed. And the colour of that precipitate will tell you whether you've got chloride, bromide, or iodide. If you get a yellow precipitate with the silver nitrate solution, you know that you have iodide ions in your solution. If you get a cream precipitate, that tells you that bromide ions are present. And if you get a white precipitate, that tells you there are chloride ions present. Going back to the first step of this testing for halide ions method, I added dilute nitric acid to remove carbonate ions. The reason for that is silver carbonate is also a white precipitate. So if in my second step I added silver nitrate solution and there were still some carbonate ions present, that might give me a false positive white precipitate and I might think I've got chloride ions when actually I haven't. The final test is for sulfate ions. Again, your first step is to add dilute hydrochloric acid to remove any carbonate ions. Now, we didn't want to use hydrochloric acid in step 2 for testing for halide ions because we would have been adding chloride ions to the solution and that would have given us a false positive as well. So that's why we use nitric acid for the test for halide ions. So back to this third test for sulfate ions, we're adding dilute hydrochloric acid to get rid of the carbonate ions. And then we add barium chloride solution. Now, barium chloride is soluble, but it contains barium ions, and that's the key here. If there are sulfate ions present, what happens is the barium ions and the sulfate ions will combine together to form barium sulfate, which is white. So if you have sulfate ions, when you add your barium chloride solution, you'll see a white precipitate form. The final thing we're going to talk about today is flame emission spectroscopy. Now, this is a method that would only be done in a lab. You wouldn't be able to do this in school. So if you had a sample containing metal ions and you heated it, the electrons in those metal ions get what we call excited and they jump to higher energy levels or higher shells. And when they return to their original energy level, that energy difference is released as light. Now you can analyse that wavelength of light and produce what we call a flame emission spectrum. Here's an example of a flame emission spectrum at the bottom for a mixture of two different metal ions. And then we have known emission spectra for different metal ions. You can see calcium at the top, copper, potassium, lithium and sodium. Now this sort of works like a fingerprint. So what you need to do is look at your mixture of two metals and the emission spectra that has given you, and you need to match up the lines on that spectra with the lines from the known metal. So if I show you here, these blue arrows are pointing from lines on the mixture to lines that are present in metal spectra above that we're comparing them to. And you can see this sort of region of lots of lines here are coming from the sodium ion spectra. You might be thinking, well, a lot of these lines actually match with the calcium ion at the top as well, but there are lines in the calcium spectrum that are not in the mixture of two metal ion spectrum, and that's how I know that it's not calcium that's one of these metal ions. So in this mixture of two metal ions, I've got a mixture of lithium and sodium ions. Okay, we're just going to do 9 quick retrieval questions based on the knowledge that we've just looked at. So your teacher will pause the lesson here and give you 5 minutes to answer these questions. Once you've finished, you can come back and we'll go through the answers. So the answers to those quick retrieval questions. Number 1, a formulation is a mixture designed to be a useful product. Number 2, the test for carbon dioxide is that lime water will turn cloudy. Number 3 would tell you that the water is not pure. If it was pure, it would boil at exactly 100 degrees. Number 4, the difference in those two tests is that hydrogen requires a lit splint and oxygen requires a glowing splint. Number 5, the RF value cannot be more than 1 because the spot cannot move further than the solvent. The colour for the potassium ions in the flame test is lilac. The colour for the copper 2+ ions with sodium hydroxide would be a blue precipitate. The way you could distinguish between those two metal ions is to add sodium hydroxide. Now they'll both form a white precipitate, but if you continue to add sodium hydroxide, the aluminium hydroxide precipitate will redissolve. And finally, the test for the sulfate ions, you would first want to add dilute hydrochloric acid to remove any carbonate ions in the solution. You would then add barium chloride solution and you would see a white precipitate form. So now we're going to look at 5 exam-style questions. So you can read through the question here on the board. Your teacher will pause the video so that you can have a chance to answer it and then come back when you've finished. Okay, so in this question, you not only had to give the test for carbon dioxide, you also had to relate that to how the student would time how long the carbon dioxide had taken to be produced. And she would just need to time how long it takes for the lime water to turn cloudy. This is question number 2. Again, your teacher can pause the video here and give you time to answer this before going through the answer. So this question was basically asking you for the definition of formulation, but in reverse, they'd given you the definition, they wanted the keyword. They also asked you to suggest why colouring was added. These are really straightforward questions. Why would colouring be added to a medicine designed for children? It's to make it more appealing or to make those children more likely to take the medicine. Question number 3. Again, your teacher can pause here. This question is a little bit longer, so you might need a little bit more time before you go through the answer. Okay, so there are 3 substances in the ink from the forged check because there are 3 dots above that in the column. In part B, they'd said to suggest why there is only 1 spot above substance B, even though it contains 2 substances. Now, sometimes if substances have very similar RF values, they will look as though they are 1 dot because they will travel the same distance up the paper or a very similar distance. Part C, describing how chromatography separates substances. This was 4 marks, so you had to give quite a lot of detail here. So your substances are going to dissolve in your mobile phase, that's your solvent, usually water, and they're carried up the stationary phase or the paper. The more soluble they are in the mobile phase, the further they will be carried up the paper before they can no longer dissolve in that mobile phase and they are left as a dot on the paper. And finally, you had to calculate the RF value. Your teacher might have had to read out these values to you. They're a little bit tricky to see, especially if you're sitting at the back of the classroom. But your distance moved by the spot was 3.3, and your distance moved by the solvent was 6.7. When you put those into the RF calculation, you get an answer of 0.49. This is question number 4. So we have a table of results here for 3 different compounds, X, Y, and Z, that have been tested using the flame test, sodium hydroxide precipitates, hydrochloric acid with barium chloride, and nitric acid and silver nitrate. You need to identify the positive and negative ion in each of those compounds. Again, your teacher can pause the video here. So looking at those compounds, compound X must contain iron 2+ ions because it gives a green precipitate with sodium hydroxide, and it must contain sulfate ions because you get a white precipitate with the barium chloride solution. Compound Y has to contain sodium ions because of the yellow flame test, and it has to contain iodide ions because it gives a yellow precipitate with the nitric acid and silver nitrate. Finally, compound Z gives a brown precipitate with sodium hydroxide, which we know indicates iron 3+ ions, and it gives a cream precipitate with silver nitrate solution, which indicates bromide ions. Our final exam style question is asking you to explain one of these tests using an ionic equation. Again, your teacher can pause the video here and come back when you're ready for the answer. So, to get a white precipitate with the dilute nitric acid and then silver nitrate, X must contain chloride ions. And the reason you get that precipitate is because the chloride ions that were aqueous and the silver ions that were aqueous combine together to form silver chloride, which is a solid. The state symbols are important here because the solid indicates that the precipitate has formed. Okay, that is the end of this session on C12 for Triple Science. Really well done. We've covered 4 topics today: pure substances and mixtures, analysing chromatograms and calculating RF values, the 4 gas tests for hydrogen, oxygen, carbon dioxide and chlorine, and testing for negative and positive ions. If you've still got a bit of time left in this lesson, you could use that to recap this content and go over those 4 topics again.